Alright, this is exam video number 4, and we're starting with problem number 8. This should be pretty familiar because it's recent material. We have a function, a cubic function, and they ask us to find the critical values of f. So as you know, to find critical values, we're going to find the first derivative of the function, and we're going to set it equal to 0. So I'll do the work down here. When we find the first derivative of this function, we will get 6x squared minus 18x plus 12. When I set that equal to 0, I can divide every term here by 6 on both sides, and I'll get x squared minus 3x plus 2. Factor to solve the equation, and I'll get x and 2 and 1 and minus and minus, so I get x equal to 2 and x equal to 1. Those are my critical numbers, x equal to 2, x equal to 1. B asks us to find where is the original function f increasing and decreasing, so we're going to make a first derivative number line. Remember to name your number line, and you're going to put your critical numbers on your number line, and that's going to divide the number line into testing regions. I'm going to choose a value out of each region. For example, I'm going to choose to the left of 0, to the left of 1, I'm going to choose 0, and when I substitute that into my first derivative, I'll get a positive 12, so I have a positive, which tells me that the original function is increasing on that interval. When I choose a value between 1 and 2, like 1 1/2 or 3/2, and I substitute that into my first derivative, I get a negative outcome, so the function is decreasing. And when I choose a value greater than 2, like 3, and substitute it into the first derivative, remember, substituting into the first derivative, I see that the original function is increasing. Now remember, the plus and minuses are what the first derivative is doing in terms of the sign. The arrows are what the original function is doing. So we can see that our function is increasing from negative infinity to 1, and then again from 2 to infinity, and the original function is decreasing from 1 to 2. Letter C, where does the original function f have a relative maximum? Well, you can see that we're going to have a relative maximum at x equal to 1, and that we're going to have a relative minimum at x equal to 2. Please remember how to write those. I'm going to write up one of those for you. We would say a relative max occurs at 1 f of 1 because the first derivative at 1 is equal to 0, and f prime of x changes from positive to negative. So that's the sentence that we're looking for if this is a show your work part of the exam. Letter D, what is the absolute maximum of f on the closed interval 0 to 3? Alright, I'm going to get rid of the work that I've done so far just to create some more space for myself. Remember the absolute maximum. Letter D is telling us to consider the extreme value theorem. The extreme value theorem says that there will be an absolute maximum and an absolute minimum on a closed continuous interval. The candidates for being the highest of all y's or the lowest of all y's occur at the critical numbers, so we have to consider x equal to 1, x equal to 2, so those are our critical numbers, and we have to consider the endpoints, x equals 0. Not sure why my pen stopped writing here. Alright, so we have the critical number of x equal to, our endpoint of x equal to 0, x equal to 3. So those are our endpoints. Now we're looking for the highest of y value, so we're going to set up a table of values. And we're looking for the output of the original function, so we have 0, 1, 2, and 3. Now be very careful because these values go back into the original function. When I put 0 into the original function, I get 0. When I put 1 into the original function, I get 2. Minus 9 is negative 7. Negative 7 plus 12 is 5. Check my arithmetic because I'm doing it in my head. 2 cubed is 8 times 2 is 16. 16 take away, what do we got here? Hold on. And if I did my arithmetic correctly, these are the y values that you get from the original function. So the absolute maximum occurs at x equal to 3, but the question is, what is the absolute maximum value? So in this case, the absolute maximum value, which is a y value, is 9. Where does the original function have an inflection point? So now we want to find the second derivative. Let me go back up here and find my first derivative again. The first derivative was 6x squared minus 18x plus 12. So the second derivative would be 12x squared minus 18, and the derivative of 12 is just 0. So I'm going to set the second derivative equal to 0, and I'll get 12x squared equal to 18. So x squared is equal to 18 over 12, which would be, if I divide by 6, 3 over 2. So x is equal to plus or minus square root 3 over 2. So if I'm going to find points of inflection, I'm going to make a second derivative number line. I'm going to put my possible points of inflection. Remember, these are only possibilities on my number line. I'll start with finding a number in between because that'll be pretty easy. I'm going to substitute 0 into the second derivative. When I substitute 0 into the second derivative, I get a negative. So that tells me that on that interval, the function is concave down. Choose a number to the left of negative square root 3 over 2. Now the easy thing to do is just choose a number that you definitely know is smaller than that, like negative 100. And so if I substitute negative 100 into the second derivative, that will give me a positive output, so the function is concave up. Same thing on the other side, choose positive 100 and I'll get a positive output, concave up. So each of these values is a point of inflection, or the x values where they occur, because the concavity is changing there. The sign of the second derivative is changing. And then you can write your intervals of concavity for letter F using that number line. Number 9, we have a table of values, and they tell us that the second derivative is always positive. So we know that on this interval from 0 to 4 that the function is concave up. And they're asking us to estimate, look at your key word here, estimate the value of the first derivative at 3. Now remember, when we were doing estimating derivatives, we have a table of values and we want to know the derivative at 3, but we don't have the function and we don't have the graph of a function. So what we did is we found the average rate of change of the 2 points. So basically we're finding the slope of a secant line to approximate the slope of the tangent line, because we don't know the tangent line, we don't know the function. So all we're going to do here is change in y, 2.8 minus 1.4 over change in x, 4 minus 2. So that will give me 1.4 divided by 2, which would be 0.7. And that would be the estimate of the derivative at 3. Problem number 10, this is very recent. We're doing linearization, and remember in calculus, well, first of all, linearization, the root word is line, and in calculus we are obsessed with tangent lines. So really all they're asking us to do here is to find the equation of the tangent line to this function at x equal to 1. So we're going to need a couple of things here. First of all, we have an x value, and we're going to need the y value. So 1 goes into the original function, and 1 squared is 1 times 3 is 3 plus 1 is 4. So the y value is the ln of 4, which is a perfectly fine number. You don't need to go to the calculator and do anything with that. So far I have y minus, substituting in my y value, ln of 4. I don't know the slope yet, but I'll get it in a second, x minus 1. So I have the first part of my equation done. Now I need to find the slope, which we know in calculus means we want to evaluate the derivative of this function at 1. So let's find the derivative of the function. It's an ln, so to find the derivative of ln, it's u prime over u. In this case, this is the u. So the derivative of 3x squared plus 1 is 6x over u, which is 3x squared plus 1. We're going to evaluate that at 1, so we will get 6 over 4, which is 3/2. So that is the slope of my tangent line. So I'm just going to come and substitute that back in place of m. And that is the linearization. That is the equation of the line tangent to the curve of ln at that point. Letter B asks you to approximate 1.2 using your answer in A. So in other words, they want us to take 1.2, substitute it in place of x, and find an output value. And you can do that with your calculator. I'm not going to, whoops. So you would get 1.2, comma, whatever you get off your calculator as the y value. And then finally in letter C, is the approximation too large or too small? Remember, that's where we need the concavity of the curve, because we need to know whether or not the tangent line is above the curve or below the curve. So to get concavity, we're going to consider the second derivative. We already have the first derivative right here. So to find the second derivative, we're going to apply the quotient rule. So we'll have down d up minus up d down over down down. And again, if you notice that I make errors in this work, which is a possibility, please let me know and we'll try to let everybody know about that. Cleaning that up, I mean, actually I could substitute the value of 1 here. I don't really have to clean that up, because all I need to know is whether I'm getting a positive or a negative outcome. Let's go ahead and clean it up. So I'll get 18x squared plus 6 minus 6 times 6 is 36x squared. We know the denominator is going to be positive regardless, so that's not a big deal. 18x squared minus 36x squared is negative 18x squared plus 6 over, and I'll just go ahead and write a positive. So when I substitute 1, you can see 1 squared is 1, negative 18. That's going to give me a negative. A negative divided by a positive is a negative. So the function is concave down, meaning that the tangent line is above, and if the tangent line's above, the approximation's too large. And we'll pick up with the next problems in the next video.